As the quest for speed and altitude continued, the Air Force, Navy, and the NACA, later NASA, contracted with North American Aviation to build a new vehicle. This new vehicle, the X-15, would probe the hypersonic speed regime, that is, faster than Mach 5, and perform flight research at the edges of the Earth's atmosphere. To perform its mission, the X-15 structure was made from a nickel-chrome alloy called Inconel X. It could retain its strength up to a cherry red 1200 degrees Fahrenheit, a temperature that would melt aluminum and make stainless steel useless. The X-15 was powered by an XLR-99 variable thrust rocket engine with a thrust range from 28,000 to 57,000 pounds. Before each flight, the pilots trained 8 to 10 hours in a ground-based simulator. The X-15's flight envelope demanded precise control during all phases of flight: the powered phase, the flight out of the atmosphere, and especially the re-entry. The pilots trained for the multitude of possible malfunctions of the rocket engine, systems, and displays. The appreciation of the ground-based flight simulator was fully realized first in the X-15 program. A flight began with the pilot climbing into the X-15 attached under the wing of the B-52 on the ramp. The B-52 then taxied out and took off, slowly climbing to 45,000 feet, heading for the northeastern corner of Nevada. Once there, the B-52 turned back toward Edwards and launched the X-15. Once clear of the B-52, the pilot lit the rocket engine and began his particular flight profile, climb for altitude, for instance, or a speed run. In spite of launching in northeastern Nevada, the X-15's flight to Rogers Dry Lake lasted an average of just 10 minutes. The engine consumed the entire fuel supply in less than 2 minutes, after which the airplane was a high-speed glider with a lift-to-drag ratio of about 4 to 1. The pilot was busy the entire flight and had very little time to enjoy the scenery. Things happened fast at Mach 5+, and this was no airplane to fall behind on. Maintaining a proper angle of attack was critical if the pilot was to reach the designated altitude. Under and overshooting were startlingly easy, and both had a dramatic effect on the final altitude reached by the aircraft. The bottom portion of the ventral fin, the vertical stabilizer underneath the aft portion of the fuselage, was too tall to permit landing with it attached. So it was jettisoned moments before landing, then retrieved and used again. The X-15 had no brakes for landing, just 2 skids that popped out at the aft end of the fuselage, and a nose gear with 2 wheels that was not steerable. The X-15 came down quickly, and its pilot had only one chance at landing, as do shuttle pilots today. For its record speed flight, the X-15 was fitted with 2 external propellant tanks, which could be jettisoned, and covered with a silicone ablative coating painted white. Unlike the shuttle tiles, the ablative absorbed the additional heating from the high speed by charring rather than insulating. Even then, surprisingly, shock impingement around a dummy ramjet on the lower ventral tail caused some serious local damage to the skins. The ablative coating proved to be impractical for a reusable re-entry vehicle, since the old coating would have to be stripped and a new coating reapplied for each flight. With flights starting in 1959 and extending to 1968, it was and still is considered the most successful of all experimental research aircraft. The X-15 program added to the historic foundation of aerodynamics, sometimes measurably, often intangibly, in ways that were not imagined. It pushed the piloted records to an altitude of 67 miles and speed to Mach 6.7. 8 of the 12 X-15 pilots earned their astronaut wings. The X-15 provided much new insight into the once feared region of flight outside the atmosphere. It also gave engineers critical data on the unique challenge of re-entry. Re-entry compounds the effects of aerodynamics and spaceflight maneuvering and proved to be more demanding of both pilot and aircraft than anything encountered before. Many of the mysteries of re-entry flight were solved by the X-15. In sharp contrast to the high speeds and altitudes of the X-15, a strange-looking vehicle appeared at the center. The low-speed M2F1, a lifting body vehicle, had no wings and resembled a bathtub. A Dryden engineer, Dale Reed, sought to validate this new re-entry concept with a manned research aircraft. Rather than using a ballistic re-entry trajectory like a Mercury, Gemini, or Apollo capsule with very limited maneuvering range, a lifting body vehicle had an estimated landing footprint the size of California. The tubby vehicle shape was taken from re-entry lifting body shapes that were being tested at the NASA Ames Research Center. After seeing Reed's 2-foot model fly, Center Director Paul Bickle authorized an in-house effort to build the manned M2F1. In the spring of 1963, Milt Thompson made the first flight of the M2F1 towed behind a hot rod Pontiac Catalina convertible. Later, an R-4D Navy DC-3 was used for tows to higher altitudes. Flights released from behind the R-4D at 12,000 feet lasted just 2 minutes until landing. The M2F1 would lead to bigger things in the future. If the M2F1 was strange, the Lunar Landing Research Vehicle was out of this world. During the 1960s, NASA had embarked on a journey to the moon. The Apollo program's mission was to land men on the moon and return them safely to Earth. No one on the Apollo program wanted the first lunar landing, with its high pilot workload and psychological stress, to be the first time an astronaut team flew a lunar landing descent profile. To help train astronauts for this difficult task, Dryden engineers Don Bellman and Gene Matranga, along with Bell Aerospace, conceived of an in-flight simulator to train the astronauts. It became known as the Lunar Landing Research Vehicle, LLRV. The LLRV was a free-flying simulator held aloft by a turbofan jet, simulating the moon's gravity, and maneuvered with hydrogen peroxide thrusters. First delivered in late 1964, the LLRV was flown by the Dryden research pilots Joe Walker, Don Malik, and the Army's Jack Kluver. During that time, the team made significant modifications to the craft, some to better mimic the lunar module in its layout, others to make the vehicle safer or more capable. Perhaps most significant of all, the vehicle was a pure fly-by-wire craft controlled by 3 analog computers with no mechanical backup. During its 198 flights at Edwards, it had flown as long as 9.5 minutes and reached a maximum altitude of nearly 800 feet. It was then turned over to Houston in December of 1966 for training the Apollo astronauts.
Picking up some dust. 4 forward.
As they say, the rest is history. On July 20th, 1969, former Dryden Center pilot Neil Armstrong set the Apollo lunar module down on the moon.
Tranquility Base here. The Eagle has landed.
The Harley-Davidson Motorcycle Company of York, Pennsylvania.
Harley-Davidson had been manufacturing motorbikes and motorcycles since about 1903. We produce most of the heavyweight motorcycles sold in the United States. We are also the last American-owned and operated motorcycle manufacturer in the country. The rest are all Japanese. When the raw steel comes into our plant, it's stamped into different parts. These red-hot struts will become part of the frame of a motorcycle. Over here, these oiled sheets will be stamped into fenders. The unfinished struts will be chromed. The fenders are painted and polished. Eventually, all the parts we make ourselves and those we buy from outside suppliers find their way onto the assembly line. Here, what starts at one end as virtually nothing becomes at the other end a Harley-Davidson motorcycle.